Hello everyone, welcome to my YouTube channel. So, like many beginners in the field of computational drug discovery, I also started my learning journey with molecular docking using Autodoc 4 and Autodoc 0. And that was the first time I came to know about the term RMSD while looking into the log file of Autodoc. As I progressed, I found that this parameter plays a crucial role in computational studies. I also find several YouTube comments and posts in different social media querying for RMSD. This prompted me to make a dedicated video on RMSD as per my understanding. The full form of RMSD is root mean square deviation, and it is used in the computational drug discovery to measure the average distance between the superimposed molecules. Okay, so let's discuss in detail. Through RMSD, the deviation or dissimilarity between two three-dimensional pores of a molecule is calculated. Suppose these are two poses of a chemical compound, one colored in green, another colored in pink. Now, if we want to compare these two poses, so there should be a measure for this, that is RMSD. So first pose, which is colored in green here, suppose is considered as the reference pose, and the second pose, which is colored in pink, it is the test pose. Now it is checked how much the second pose is different or dissimilar from the reference one. Okay. So now the major question is, how is it calculated? Okay. So let's see. Now we have with us three poses of a same chemical compound. This is the first pose, second pose, and third pose. And I am opening the first pose in visualization software, that means Biovia Discovery Studio. Okay, so this is one pose, and you know the molecule consists of atoms. Okay, so these are the atoms: carbon, carbon, carbon. This is hydrogen. This is oxygen. This is nitrogen. And left side, you can see what are the component atoms of this molecule: carbon 1, carbon 2, nitrogen, carbon 3, carbon 4. Okay, so these are the atoms of this molecule. Okay, and each atom has its 3D coordinate. That means a position in the three-dimensional space. Suppose in case of this hydrogen atom, it has its 3D coordinates: x coordinate, y coordinate, and z coordinate. Okay, for proper visualization of each atom, I am changing from stick to ball and stick. Okay, I am opening the second pose. Now I am copying its coordinates and pasting it to the hierarchy of another pose. So now these two poses are present in the same visualization panel, and I am coloring the two poses in two different colors. The first pose in green color, and the second pose in yellow color. This is the hydrogen 9 of second pose, and this is the hydrogen 9 of first pose. Okay. In second pose, the hydrogen atom has shifted from its initial position. There is a change in its coordinate. So now we can calculate the deviation, how much it has shifted from its initial position. Similarly, for each atom, we can calculate the deviation. Okay, so we can compare the deviation from carbon 1 to carbon 1, carbon 2 to carbon 2, deviation for each atom, present in first pose and second pose. Suppose a molecule consists of 4 atoms, 3 carbon atoms and 1 nitrogen atom. And now we are comparing the RMSD between two poles of that molecule. So deviation between the first carbon atom of two poses is first calculated, then it is squared. Then the deviation between the second carbon atom of the two poses is calculated, then it is squared. Similarly, for the rest of the atom, the deviation is first squared and these deviations are added, and then it is divided by the total number of atoms. That means a mean value or average value is first calculated. Then the root of that mean value is calculated. That is RMSD, root mean square deviation. Okay, so if the root mean square deviation is under 2 angstrom, it is usually considered that these poses are very similar. Or if the RMSD is above 2 angstrom, then it is considered that their two poses are quite dissimilar. Okay, so now let's see what is the RMSD between these two poses. So after superimposing these two poses in Biovia Discovery Studio, we can calculate the RMSD between these two poses. So go to the structure and then click in this option RMSD. So you can see that the first pose is the reference pose whose RMSD is 0. That means it is not compared with anyone. It is itself a reference pose. But the second pose, its RMSD is 1.9. It's under 2 angstrom. That means this pose is very similar with the reference pose. Slightly dissimilar, but quite similar. This is the third pose. I am opening it in Biovia Discovery Studio. Now, three poses are present here. Now we can calculate the RMSD. Go to the structure, RMSD, all atoms. So you can see the reference pose RMSD is 0 and the second pose is RMSD is 1.90 and the third pose, which is quite dissimilar, its RMSD is 9.03 because it is present slightly away from the first two poles. So one important thing, now these two molecules are not moving, they are fixed. Okay, but during molecular dynamic simulation, this molecule will move continually. Okay, so the coordinate of these atoms will also change in every moment. So for each moment, we can calculate the changes in RMSD value. So we can calculate the RMSD deviation for each moment or each step. You can see here, this ligand is continuously changing its position. That means its RMSD value is also changing. Okay, now we can plot these RMSD values to get a graph, of the RMSD trajectory. And this RMSD trajectory graph is obtained in molecular dynamic simulation. I am showing you a RMSD trajectory. So you can see, this is a RMSD trajectory of one chemical compound. Initially, its RMSD was 0 when it is compared with the reference. Then gradually its RMSD is changing, and after some time, approximately after 10 to 20 nanoseconds, its RMSD becomes stable. Okay, now you can see its RMSD range is between 0.2 to 0.3 nanometer. So the ligand becomes stable and it remains stable throughout the simulation. Its RMSD ranges is now between 0.2 to 0.3 nanometer. And this is the fluctuation. That means its RMSD is changing but slightly. Okay, so now we can say this molecule is stable. Okay, so in upcoming tutorial, I will explain how to perform molecular dynamic simulation to track the changes in the pose of any biomolecule or changes in the conformation of the biomolecule. So in real time, to track this, molecular dynamic simulation should be performed. Okay, so that's all for today's tutorial about RMSD. Thank you. Thank you for watching.